All right, so let's continue our discussion on transonic and supersonic flows. So this lecture, we actually have a lot of stuff to cover, so we'll get through some material pretty fast, and there is certain sections that I would normally let you work on it, but like due to lack of time, we'll just work on my screen instead. Okay, so the first thing is that we started looking at a shockwave at the last lecture, right? And the shockwave decelerates the flow from supersonic flow back to subsonic flow. But a shockwave does so in a way that is very different from an isentropic process. So let's actually consider how they differ, all right? So imagine, first of all, we have a flow that is symmetric in the sense that it accelerates from Mach less than 1 through this converging then diverging streamline geometry to Mach number greater than 1, right? So last lecture we learned that when the Mach number is equal to 1, no matter what the flow does, no matter if it keeps accelerating or decelerates, the geometry, the area of the stream tube has to expand, right? No matter if the flow decelerates or accelerates. So basically that says that Mach 1, the choke point, has to be the area, has to be the minimum stream tube area, all right? So basically when the Mach number, when the flow further accelerates, the stream tube has to expand. Now consider two alternatives. The first alternative, let's mark it as green, is that we have exactly the reverse process. So let's say the geometry is designed perfectly symmetric to the upstream case, and there is no viscosity at all, right? In this case, the flow would basically slowly decelerate. Up to this point, we have Mach equal to 1, and then up downstream, we have back at subsonic conditions. The other case, let's use purple, is that the geometry stays constant, okay? And we get the shock wave. And after the shock wave, we also have Mach less than 1. So let's apply some conservation laws to analyze what's really different between the two cases. All right. Okay. So, and basically the control volume goes from here all the way to here. So basically, let's actually just put it over here. So it goes from here to over here. So basically, we look at the region that goes from the supersonic flow to subsonic flow, and the area of the area of the inflow and outflow is exactly the same. So first of all, between the two cases, the green and purple case, does the conservation of mass be any different? The conservation of mass is exactly the same, right? The inflow area is the same, the velocity and density of the inflow is the same, and assuming the Mach number downstream is the same, then the outflow of mass is also exactly the same. How about conservation of energy? Is there any difference in the conservation of energy? Yes? How is it different?
Since there's a shock, isn't some energy lost due to the shock?
Okay, good point. It's some energy lost due to the shock. So if the energy is lost due to the shock, where does the energy go?
Sound.
Okay, so if there is sound energy, where is that sound energy go, right? Where is it? It still has to come out of here, right? So some energy is converted to heat, right? Some energy may be converted to sound, but like it comes out of here. So the conservation of energy equation is actually not different, right? So if, for example, you assume that the density, pressure, temperature, velocity, Mach number, and everything downstream is the same between the green case and the purple case, then the outflux of energy should actually be the same, right? It doesn't differ from the influx of energy from the upstream, right? Okay, so basically, still up to now, no matter if we consider conservation of mass or conservation of energy, right? It is perfectly reasonable to say that no matter if the deceleration is through a shock or through a conversion-diversion nozzle, the outflow quantities could have been exactly the same. All right? Because the conservation of mass and energy equations are the same. Now, the only thing differs is the only other conservation law. What is that? Momentum, exactly. So how is the conservation of momentum different between the purple case and green case? Anybody see the difference? Is there an extra term in the conservation of momentum in either the purple case or the green case? Just a hint. If there is no difference, then rockets won't work. Right? What does a rocket nozzle look like? Like a conversion-diversion channel, right? I mean, why is there such a conversion-diversion channel? Like, what is the function? Or what is the purpose of designing a conversion-diversion channel on the rocket? Increase the thrust, right? Okay, so that means there is a force, there is an external force, in which case? Green case or purple case? The green case, right? There is an axial force due to the difference in the pressure between the convergent section and divergent section. Which section has higher pressure? The subsonic section or the supersonic section has higher pressure? Somebody? The subsonic section has higher pressure, right? So what is the total force from the fluid to the, just to think of it as a rocket nozzle, right? As actually, this is like a reverse rocket nozzle. This is like a rocket nozzle where the flow in the combustion chamber is subsonic, and then the nozzle accelerates the flow to supersonic speed, right? So this is like a reverse rocket nozzle, and what is going to be the force from the fluid to the nozzle? In which direction? That direction or that direction? That direction, right? Because high pressure here, low pressure here, right? Okay, so that means the rocket nozzle applies a force to the fluid in the opposite direction, right? It applies a force in that direction to the fluid. Is that force there in the purple case? No, right? Because the area is constant. So the conservation of mass and the energy equations are the same, but the conservation of momentum equation has an extra term in the green equation, in the green case. That means the state at the outlet cannot be exactly the same for the green and purple case, right? So this is fundamentally why, like the deceleration by a shock cannot be asymptotic. All right, the solution has to be different. Now, if you solve these three equations, this is what you actually get. The So this table, you can look it up from a lot of sources. They'll show you the same thing, but I'll tell you how to read them. So look at these blue arrows. So this has to be looked at on the left axis, right? So the M2, which is the Mach number downstream, as the M1, which is the Mach number upstream, increases, the Mach number downstream decreases. All right. The other line that looks at the left axis is the stagnation pressure loss. That's the ratio of the stagnation pressure. So that's the most important quantity, probably. Because if you look at the green case, the isentropic deceleration, what is the ratio of stagnation pressure between the downstream and the upstream flows? It's the same, right? The ratio is equal to 1. Right? No, there's no viscous forces, right? So the stagnation pressure, even for compressible flows, should be exactly the same, right? So that's our generalization of Bernoulli. We worked on it. I think we worked on it during the 3rd week or something in our homework, right? But when you across a shock wave, there is viscous forces. The shock wave is very, very thin, right? Just like a boundary layer. And the velocity changes rapidly from before the shock and after the shock. So viscous forces actually works within the shock that introduces a loss in the stagnation pressure. That is why when you look at this line, right, it goes down, which means the downstream stagnation pressure is always lower than the upstream stagnation pressure. Another feature that's noteworthy is that the line of the stagnation pressure is tangential, is horizontal at the Mach equal to 1 point. Come on, yeah, at this point, right? So the line is horizontal, which means when the shock is very weak, which means when the upstream Mach number is just slightly greater than 1, and the downstream Mach number is only slightly less than 1, right? The loss in stagnation pressure is very small. So basically, a loss in stagnation pressure is negligible if you have a very, very weak shock. And we'll see how that is going to be very important when we start looking at oblique shock waves. All right. So the other two quantities should be looked at towards the right. One is the ratio of pressure, right? Because as you pass a shock, the stagnation pressure drops, but the static pressure would increase. Another thing is the temperature also increase. So these two quantities are not really shown in many of the tables because you really only need these two quantities. Because the static pressure and the static temperature can be just computed according to like the formula, right? The formula that relates the static pressure to stagnation pressure, and the formula that relates static temperature to stagnation temperature. And the stagnation temperature is not shown over here because stagnation temperature does not change across a shock wave. This is actually a consequence of conservation of energy, right? So if you imagine a stream tube that decelerates isentropically back to isentropically from supersonic back to subsonic and then all the way to 0 velocity, versus another stream tube that goes through a shock to subsonic and then again slow down to almost a 0 velocity. As I said, the conservation of energy equation is exactly the same, right, between these two cases. So stagnation temperature, which relates to how much temperature is there at the end of the deceleration to almost a 0 velocity, is the same because at that point, all the energy is actually in the internal energy, right? So that's basically how the stagnation temperature is defined. It's basically when the stream tube decelerates to 0 velocity, what is the temperature, of the fluid. So no matter if no matter if we're decelerating through the green case isentropically or through a shock, and then further we decelerate to zero velocity because of conservation of energy, the stagnation temperature is the same. So if I draw an additional line over here, that'll be TT2 over TT1. It just stays as 1, doesn't change. All right. So basically, if you in the future you need to look up normal shock tables, just the two lines pointing towards the left are probably the most useful. And basically, actually you can also compute the Mach number from the stagnation pressure drop, but the formula is kind of relatively complicated. Essentially, there is only one equation that you need to solve numerically. All the other quantities can be just computed using analytical relations. All right, any questions regarding to this graph for now? Yes, no? Yeah?
I still don't quite understand why the stagnation pressure changes. You said the ratio is equal to 1.
The stagnation pressure or temperature?
The pressure.
Yeah, the pressure ratio is not equal to 1, right? This is the ratio of the stagnation pressure. So when you have a very weak shock wave, you see this line is tangential to the horizontal axis, so the stagnation pressure loss is very small. But as the Mach number becomes significantly higher than 1, there is a significant loss in stagnation pressure. Yes, right. All right, and by the way, this line is Mach 1.5. This line is Mach 2, right? So if you have a Mach 2 shock, you have more than 40% loss in. Mach 2 shock. You have actually no, you have almost a 30% loss in stagnation pressure. All right. Any other questions? All right. If no, let's actually start to look at why a lot of the transonic airplanes have swept wings. Okay, this is because the fundamental difference between a shock wave that's normal to the flow direction, which is what this table shows, right? This table shows like the basically just from the one-dimensional conservation loss, which means the whole velocity is normal to the shock. If we have a swept wing, what's happening is that if you look at the CFD calculations for two airplanes, one has a straight wing, one has a swept wing, right? You can clearly see that the swept wing have a oblique shock wave. So the shock wave is actually not normal to the flow direction like this one. So why is it advantageous to have an oblique wing that creates an oblique shock? So let me just go through a very simple example to demonstrate that. Okay, so this is titled "How Strong is an Oblique Shock?" I would have let you work on this, except for we don't really have that much time, so we'll work on it on my screen to see what we get. So let's imagine we have an airplane that flies at Mach 3, okay? And just imagine we have just the standard, okay, so let's say standard atmosphere, 100,000 pascals, and a 30-degree oblique shock. So what does that mean? That means the oblique shock, right, has an angle of 30 degrees. And before the shock, we have a Mach 3 flow. First of all, let's take a look at what happens if we have a normal shock at Mach 3. Go back to the graph. We can see that at Mach 3, the normal shock would be very strong, right? So particularly if you look at the ratio of stagnation pressure. Almost we are losing 2/3 of the stagnation pressure at upstream, right? And essentially what that means is a lot of the mechanical energy is converted to thermal energy across a Mach 3 normal shock. And the resulting drag on the airplane, so basically how much energy would have to be provided by the airplane to how much mechanical energy has to be provided, for example, by thrust to make that much thermal energy is going to be enormous. But let's look at how an oblique shock is going to change a lot of that. All right, so for example, let's first look at what are the tangential and normal velocity components of a Mach 3 shock. Right, so if we decompose that velocity into a velocity normal to the shock and a tangential to the shock, what is the component normal to the shock? Any? Oh, we have a 30-degree angle, right? What? What times the Mach? Yeah, sine of 30 times the velocity, right? And the sine 30 is 1/2. Okay, good. All right, the normal velocity is 375 meters per second, right? And then the tangential velocity is, anybody can compute square root of 3 for me? What is the tangential velocity, right? The cosine of 30 degrees times. Okay, and would you mind? Good, you don't have to use a calculator even, right? What is the tangential velocity? Anybody can just give me an answer? About 500. All right, let's just say 500. Okay. Now, what are the tangential and the normal Mach numbers? So we'll just consider, instead of Mach 3, right? We'll just say, okay, the Mach number in the normal direction is going to be 1.5, right? In the tangential direction is 1.5 times square root of 3, which is going to be what? 2 point what? 4, 5-ish. All right. Okay, so it doesn't matter. All right. Somebody did the math for me. What is 1.5 times square root of 3? All right. Okay. 2.59, 2.6. Okay, good. Thanks. All right. So now this is basically a preparation for what's happening after the shock. So consider conservation of mass and momentum tangential to the shock. So conservation of mass doesn't have a direction, right? So if you draw a control volume that's very thin and just crosses the shock, what is the mass flux into the control volume? It is the density before the shock times the normal velocity, right? Okay, that has to equal to the density after the shock, which is changed, times the normal velocity after the shock, which is also changed. So that actually is a minor concern. So basically, rho times u1, let's say u normal 1 times is going to be equal to rho. Sorry, maybe I shouldn't use this color. Let me use this one. Okay, so rho 1 times u normal 1 is equal to rho 2 times u normal 2. All right? Okay? So, what is the conservation of momentum tangential to the shock? By tangential to the shock, I mean in this direction. What is the influx of momentum in that direction? Yes, into the control volume. What is influx? Huh? It's infinitely thin. Zero? Yeah, the tangential component of momentum. Yes, it is equal to the mass flux times the tangential velocity, right? So this is that mass flux. Okay. So the u times un1 times u tangential 1. So that's how much momentum, tangential momentum, has gone into the control volume. How much tangential momentum has gone out of the control volume? Similar, right? So that's rho 2 times un2 times ut2. Agreed? Okay. Can I just say these two are equal? Conservation of momentum? No? What am I missing?
There's an extra force.
There is a force, right? Okay, now let's look at what tangential force is applied to this infinitely thin control volume. What is the force in the tangential direction? What are the forces? Somebody think about it. Well, in this flow, this control volume doesn't touch any solid bodies, right? So there is only forces within the flow. There is viscous force and pressure force. First of all, viscous force is non-negligible within the shock. But here I have carefully drawn the control volume so that both sides are actually outside of the shock, right? So there is actually no viscous forces except for maybe at just at this point, right? But this point is going to be so small that probably doesn't matter. I've drawn this to be very thin. How about pressure force? Now, pressure force is not going to be zero because the pressure upstream is going to be a lot lower than the pressure downstream, right? Across the shock, the pressure always increases. But which direction is the pressure force? It's normal to the shock direction, right? Because I've carefully drawn the control volume so that it is infinitely thin, and also if the shock is uniform, whatever pressure force in the tangential direction is going to cancel out. So the pressure force is also zero in the tangential direction, right? What does that mean? That means these two are actually equal. And this is non-trivial because we have to actually look at external force, and just in this case, the external force does not happen in the particular direction we are looking at. Now, just to combine these two equations to see what that means. Can anybody see a very remarkable conclusion from these two equations? So, rho 1 un1 is equal to rho 2 un2. Rho 1 un1 times ut1 is equal to rho 2 un2 times ut2. What conclusion can we draw from these two equations? Yes, ut1 is equal to ut2, right? Because from this equation, this is equal to this. So this has to be equal to this. The tangential velocity does not change across a oblique shock, right? So this is, again, if you remember anything about oblique shock, this is probably the thing you should remember. Okay, tangential velocity, no matter in which tangential direction, does not change across an oblique shock. Now, not only is this conclusion very important, the most important thing to remember, but also it has very significant consequences. That is, the most significant consequence is the following. Now imagine, instead of choosing the frame of reference relative to the airplane, what if I choose a frame of reference that moves along the shock wave with a velocity of ut1 or ut2? I mean, it's the same, right? So imagine I'm moving along the shock wave. So the shock wave stays stationary with me, right? But I am moving across, I'm not across it, but along it. How would the different frame of reference change the velocity vectors? Okay, what is going to be the velocity upstream of the shock if I choose a different frame of reference? How would this Mach 3 velocity change? I would only see the normal component, yes, because my frame of reference is moving with the same velocity as the tangential component, right? Okay, how about the flow after the shock wave? What direction is the flow after the shock wave? Still normal, right? Because ut1 is equal to ut2, right? I'm moving at the velocity, and that velocity is the tangential velocity both upstream and downstream of the shock wave. So effectively, I have converted, just by changing a frame of reference, I have converted an oblique shock into a what? A normal shock, right? Now, the flow both upstream and downstream is orthogonal to the shock front. Yeah, right? Any questions regarding to what I'm doing here? Okay, now we have a normal shock. And what is the upstream Mach number of the normal shock?
Five.
1.5, right? That's why I pasted this table here, right? Because oblique shock is normal shock. There is no difference. The only difference is a different frame of reference, right? So oblique shock is normal shock. All right. Okay. So 1.5 is this point, right? And we know that this is what? Okay. Now the Mach number downstream is going to be 0.7, and that means the Mach number in the normal direction, right? And we also know basically everything, right? The temperature, pressure, etc., right? And what is the pressure after the shock, right? Would you tell me that? How do you look up what is the pressure after the shock? $15,000? Oh, what? So sorry. Upstream we get 100,000 pascals static pressure, right? And the downstream, this is the Mach 1.5 normal shock, right? Downstream, this is the P2 over P1. It's about 2.5, right? So 2.5 times this, maybe 250,000 pascals, right? Basically, that's how you use a normal shock table for oblique shocks. Yes, question?
Sorry, can you repeat how you read that in the table, the pressure after the shock?
Oh yeah, how I read that in the table. So basically, there are 4 lines, right? And this line and this line refers to the left coordinates, and this line refers to the right coordinates, right? So basically, when you look up for P2 over P1 is this line, so you refer to the right. And the x-axis is the M1, which is the Mach number before the shock. And if you have an oblique shock, it's the normal component of the Mach number upstream of the shock. In this case, it's 1.5, right? So if you look at this line at 1.5, you look at the right coordinate, that is 2.5. Times the original, right? So this is a P2 over P1. Alternatively, you can look on the left of this thing. So that's the stagnation pressure ratio, right? And if you have a stagnation pressure ratio of 0.93, you can multiply the stagnation pressure ratio by the ratio of 1 plus gamma minus 1 divided by 2 times m squared parenthesis to the power of gamma over gamma minus 1, right? That's kind of the ratio between the stagnation and the static pressures. You both know the M1, 1.5, and M2, which is 0.7, right? So you can do the calculation that way. That'll get you exactly the same line as this, right? So if you happen to have a table that only have the left axis, then you have to do some calculations. All right, any other questions regarding this? Good. Okay, so basically what that means is that by designing, for example, a wing that has a high sweep angle, right, that sweeps back by 60 degrees in this case, so that you get a 30-degree oblique shock, I have essentially avoided the super strong Mach 3 shockwave. Instead, I have a much weaker Mach 1.5 shockwave, right? Basically, that is the value of a swept wing. So you see, like the transonic airliners has just a slightly swept wing. Well, because they're not flying at Mach 3, right? So this jetliner might be flying at, let's say, Mach 0.8, which means the maximum speed on top of the wing might be, well, Mach 1.2, right? By sweeping it back a little bit, you basically get a cosine of the sweep angle multiplier on the upstream Mach number. So if the highest speed is 1.2, and then this cosine angle is just enough to make the Mach number just slightly above 1, right? So you get essentially a very, very weak shock that basically has negligible pressure loss. So that's how normal airliners flies at transonic speed without really incurring any noticeable increase in their drag, because they do have shocks, but their shocks are so weak that it doesn't really affect the overall performance. All right, questions on that? No? Then we are going supersonic now. All right. Okay. So how do we design airplanes at supersonic speeds, right? So as you see an example, this is like a subsonic airplane, and as we exceed the Mach 1, the drag increases from the drag coefficient increases from on the order of 0.01. Basically by an order of magnitude, right? So that's not something we really want at supersonic speeds. And to understand how do we design airplanes at supersonic speeds, we need to understand the dynamics of this kind of flow fields. This is qualitatively different from what we have at subsonic speeds. All right, so basically, if you look at the flow field, right, we have this kind of oblique lines that emanates from the airplane. And let's just focus on understanding how these things actually forms. So to understand this, let's actually first, I'm going to first show you like a dramatic simplification of the equations we are encountering at supersonic speeds, and that basically reveals like why the flow field is dramatically different. Okay, this simplification is what's called the small disturbance theory. So that is assuming that most of the flow field goes in the free stream direction, and whatever difference we have between the flow velocity and the free stream velocity is much less than the free stream velocity itself. So this is basically the same assumption we are making thin air flow theory, right? Except for we have now supersonic speeds. So if we make that assumption, how does the conservation of momentum equation become? So the conservation of momentum equation, for example, in the x direction is rho u times du dx, right? Again, we are looking at steady state. Plus dp dx would be equal to 0, right? And to make things easier, let's just make some non-dimensionalizations. Let's make a u tilde defined as velocity minus u infinity divided by u infinity. All right. Okay. And we are going to ignore the difference. Basically, u tilde is going to be much less than 1, right? So basically, the difference between u and u infinity is much less than u infinity itself. And v infinity, let's define it as v divided by u infinity. And again, v infinity is going to be much less than 1. And if you have w infinity, it's the same. But just for the sake of speediness, let's just think about it in 2 dimensions for now. Okay. This equation basically becomes... And also the difference between rho infinity and rho is going to be small. So basically, what happens is that if you write rho as the difference, as basically the sum of 2 terms, rho infinity plus rho minus rho infinity, right? The second term multiplied with this, because du dx by itself applied du dx by itself, because u infinity is a constant, so that by itself is a small number, right? So this multiplied with other small numbers is going to be negligible. So basically what you get is rho infinity u infinity times du dx plus dp dx is equal to 0. So here we also just do a non-dimensionalization of p tilde. So p tilde is going to be p divided by p infinity. I'm going to divide it by a further factor of 1.4. Just the equation I end up getting is going to be a lot prettier if I do this. Okay, so once I do that non-dimensionalization, what I can do is I can divide by another u infinity on both sides. So I have u infinity square over here, right? And the u becomes u tilde, because this is sorry, I'm multiplying u infinity, then divide by u infinity, right? U divided by u infinity is equal to u tilde, right? There is a constant term which doesn't matter when you're taking derivatives. And the p, if you transfer that into p tilde, I have to multiply by a gamma p infinity, right? Okay, got it? Now, let's just get rid of these terms by dividing both sides by divide both sides by gamma p infinity. What do I get? So if I divide it by gamma rho infinity, this is gone, and this is gamma p infinity. What is that thing? Mach squared, right? So I have m squared, m infinity squared, really, times this is equal to 0. All right? Good. I'm going to have a similar equation. If I look at the y momentum equation, I'm going to have m squared times d dv tilde dx. So that's the y momentum equation, is going to plus dp tilde dy. That's going to be equal to 0. So that'll be the y momentum equation. And you can derive it essentially the same way. And then third equation is conservation of what? Conservation of mass, right? So sorry, what are you laughing at? Okay, so conservation of mass gets us in 2 dimensions. It's the derivative of rho u dx plus the derivative of rho v dy is equal to 0, right? And that means if I just split them out, what I get is each derivative has 2 terms. One term is just the rho times du dx plus dv dy. And another term is u times d rho dx plus v times d rho dy, but v is going to be so small that it doesn't matter. And the difference between u and u infinity is also so small that this doesn't matter, right? I can basically change this to u infinity and change this rho to rho infinity without neglecting any first order terms. I'm only neglecting the square of small numbers. All right? Okay, and again, we can change these dimensional quantities to tilde values by dividing just the whole thing by u infinity. So if I'm dividing this by u infinity, what I get is that this u infinity is gone. Oh, sorry. This u infinity is gone, and these v and u values becomes tilde values. 1 second, am I missing anything? So this is right, yeah, okay, so not missing anything yet. And let's just also divide both sides by rho infinity. So what I would get is times 1 over rho infinity. And remember the fractional derivative. Oh, okay. So there is a subtlety here. That is, when I have small disturbances, the shock waves, the oblique shocks, are also going to be infinitesimally weak, right? So basically, what I'm assuming is that the flow velocity before and after the shock is very small, infinitesimally small. That also means the shocks are infinitesimally weak. All right, and the pressure loss, the stagnation pressure loss across the shocks are also going to be very small. What that means is isentropic assumptions actually work here. So d rho over rho would be equal to 1 over gamma times dp over p, right? So that's like our isentropic relation on fractional sensitivities. And basically dp over p also divided by gamma is actually equal to dp tilde. So basically the whole thing on the right hand side, d rho dx divided by rho infinity can be written as, maybe I shouldn't say equal here. I just because I already did manipulations to the equation, right? So 0 is equal to this, and the d rho over rho is basically going to be it's the same as dp tilde dx. Okay, so we have 3 very simple equations. So m squared times du tilde dx plus dp tilde dx is equal to 0. M squared times dv tilde dx plus dp tilde dy is equal to 0, and du dx plus dv dy plus dp dx is also equal to 0. Yes?
How did you go from the rows?
Yeah, I go from rows to the p's by basically d rho dx over rho infinity is equal to 1 over gamma times dp dx divided by p infinity, right? So that's a isentropic relationship, right? And this, by the definition of p tilde, this is dp tilde dx. So this is p tilde definition. All right. Okay. Yeah. So basically, let's mark our 3 equations. And if you have 3 dimensions, you just have one other equation that is m squared times dw tilde dx plus dp dz is equal to 0. Okay. So these are set of linear equations, and the set of linear equations actually, if you combine them, has a very interesting property. It completely changes a behavior when the m square exceeds 1. So when the m square is less than 1, the set of equations form what's called a elliptic set of partial differential equations. If you start to, I think if you study partial differential equations, this is probably the first thing you're going to learn is when you have linear partial differential equations, right? The distinction between elliptic type, parabolic type, and the hyperbolic types. So here, in this case, when m squared is less than 1 subsonic, we have elliptic partial differential equations. And the nature of elliptic partial differential equations is basically represented by the most commonly known elliptic partial differential equation, the Poisson's equation. So that's the same equation when we, in the incompressible flow, right, we introduced that tells you what is the, well, I don't remember if we did introduce it, but like if you have, we actually wrote the divergence-free condition for velocities and said that the velocity is equal to the gradient of the velocity potential, right? If you combine these equations together, you're going to get the divergence of the gradient of the velocity potential is equal to 0. That's the archetypical elliptic partial differential equation. And the nature is that if you make a geometry, right, the effect of the geometry is going to propagate upstream, downstream in all directions. That's what happens with elliptic equations. What happens with hyperbolic equations is what happens when the Mach number exceeds 1. For hyperbolic equations, our typical hyperbolic equation is the wave equation. Is what happens when you throw a stone into a pond. The wave that emanates from the location of the stone entering the water, right? The wave kind of propagates outwards. That's what happens for a hyperbolic set of equations, is that you see definite waves. And this is what you see over here. And but the difference is that instead of propagating in time, this set of equations, they propagate in the direction of the free stream. So it is like if you take a cross-section of the air and let the cross-section move through the airplanes, or better, if you think if you have a cross-section of air that's staying with the ground, and you have an airplane that flies through it, okay, you're going to see the waves of velocity and pressure propagate on this cross-section, just like you throw a stone into a pond. So let's actually look at it. So this is let's actually look at a video of what actually happens. So let me actually make it maybe goes right. So sorry for that. Let's actually make it go slowly. Is there a way to make it go slowly? Yeah. Okay. So if you look at slowly, basically we have a cross section and we are showing pressure. The cross section moves downstream of the airplane. What we can see is that as the nose pierces the cross section, we clearly see a ring of wave, right, emanating out from the location where the nose pierces the cross section. And here we have another pair of waves starting from the leading edge of the swept wing, right? So we can see these also now propagate out. And when the wing ends, we have further a set of rings propagating outwards. And when the fuselage ends, you have yet another wave that comes out. So, by the way, like when a supersonic airplane flies by, what you hear is a set of distinct sonic booms, right? And the most common, you hear two sounds. You hear bong, bong, right? I mean, the first bong is the wave coming from the nose of the airplane. The second bong is from here, right? When the flow converges back on the tail, that creates another wave that comes out. Yes? Questions? No? Okay. And the angle of the waves is actually quite interesting because this is at Mach 1.4. And the angle of the waves is actually coincidental with the angles of the waves are basically going to be smaller as you are looking at a higher Mach number. So this is Mach 2.4, and if you look at how different this case is, why don't I? Okay. If you look at a higher Mach number, you're going to see the waves are actually propagating a little bit slower. One way to think about it is that the airplane is traveling faster, right? So as the airplane is going by, the waves doesn't have as much time to propagate out. So the angle of the waves are going to be smaller. And we're going to calculate exactly the angle of the waves a bit later, right? So that's how you see this triangular shape, because the wave actually propagates at a slower speed than the leading edge of the wing actually coming through this particular cross section. Yeah, question?
Does the wave propagate out at the speed of sound?
Yes, the waves propagate out at a speed very close to the speed of sound. You can actually calculate that for very weak shock wave. Let me actually do this calculation over here. All right. Yeah. So when you have an airplane, when you have an airplane, you are flying by. So let's just say you have this airplane flying by, and you have waves propagating out. These are basically oblique shock waves, right? And if you have if the oblique shock wave is very weak, that means the Mach number, if you decompose the speed into tangential and normal directions, the Mach number normal to the shock is going to be barely above 1. And the Mach number after the shock is going to be barely below 1. Right? Now, let's just imagine the normal component is actually equal to 1. What does it say about the entire Mach number and this angle, right? So let's say the angle of the waves are theta. So if the normal component is 1, how does that tell you about the relation between m and theta? Just from geometry, if this angle is theta, right, then this angle is also theta, right? This is also theta, and this angle is also theta. That means mn over m, which is 1 over m, is equal to what? Sine theta, right? Right, this angle is theta, right? Because this is theta, this is theta. Agreed? Okay, so basically the higher Mach number we have, the smaller sine theta we have and smaller theta we have. Okay, and this analysis can also tell us what actually determines the pressure at supersonic speeds. So this has to do with how the angle would change, how the flow angle would change after it passes the shock wave. So as we said that the tangential velocity would not change, right, when you are crossing a shock wave, but the normal velocity does change. And the normal velocity would increase or decrease after you pass a shock wave. Decrease, right? Now the normal velocity decreased while tangential velocity does not change. The flow direction would turn in which direction? Would turn up, exactly. Would turn up. And similarly, on the bottom of the airplane, right, if we have a similar shock, which direction would the flow turn? Would turn down, right? Okay, so these are symmetric. So let's just analyze one side of the flow. Again, assuming this angle, let's say phi, okay, is going to be much smaller than 1 because the shock is very weak. How can we relate the angle to the change in velocity? That's a purely geometric question, right? So again, let's actually zoom into here a little bit more and draw this geometry here. So this is the change in the angle phi, and we have a shock wave that's having an angle of theta, right? So this angle between them is going to be theta minus phi. Okay, and we have the upstream velocity of so let's say the velocity is u infinity and m, okay, and then the normal component would be, so this is theta, this is theta, the normal component would be u infinity times sine theta and m times sine theta, right? The tangential component is actually going to be the same no matter if you look at the downstream or upstream. It's u infinity times cosine theta, right? So let's just actually the Mach number is different from upstream to downstream because the temperature changes, the speed of sound actually changes. So we can only for sure that the velocity stays the same in the tangential direction across the shock. All right, so how does that relate to the velocity downstream? So again, downstream we have an angle that's changed a little bit, right? So the tangential component is exactly the same, but the normal component decreased so that the angle would be theta minus phi. Okay, so that means the normal component is going to be the tangential component times what? Right, this angle is theta minus phi, right? And this is the tangential component that didn't change, and this is the new normal component. We have a tangent, right, of theta minus phi. right? Okay. Okay, and well, anybody remember the derivative of a tangent? Good. Okay, so tangent theta minus phi is approximately, so this is when phi is very small, right? Is equal to tangent theta plus 1 over cosine square theta times the small change phi. Right? So this is basically using the derivative of a tangent, and that's what we call a first order approximation, right? Do Taylor series expansion and only keep the 0th term, which is tangent theta, and should be minus, and the first order term, which is minus phi divided by cosine square theta. So plug this in, the normal velocity downstream can be written as a function of phi, right? It is going to be equal to u infinity times cosine times tangent, which is going to be a sine, and then minus u infinity times cosine divided by cosine square. So we have a u infinity divided by cosine theta times phi, right? And in particular, this is the normal velocity before the shock. So this is exactly how much we have slowed down, right? So this is the delta normal velocity. So how is that useful? It is useful because we can now plug this into the conservation of momentum equation and figure out how much the momentum flux in the normal direction has decreased. Right? So if you draw a very thin control volume along the shock, right, we know how much the velocity decreased, right? And we know the momentum flux is the mass flux times the normal velocity, and mass flux is the same, right? Conservation of mass flux is the same in here and out of here. So that mass flux times the normal velocity before the shock, u infinity sine theta, minus the same mass flux times the velocity normal after the shock, which has been changed by this, right, is the difference in the momentum flux in and out. What is going to balance that difference? What makes up for the less momentum coming out of the shock than the momentum that goes into the shock? Force, right? What force? Pressure force. That's exactly why the pressure has to be higher after the shock than before the shock, right? Because there is less momentum coming out. The velocity decreased. So from this delta V, we can figure out exactly how much the pressure has to rise after the shock, right? And that's going to be related to the angle. So as we're going to see, we are going to be deriving a linear coefficient that relates how much the pressure has increased to how much the flow has turned. And how much the flow has turned is related to the geometry, right? I mean, if you have an airplane whose nose has an angle equal to 2 phi, right? Have phi on the upper side, phi on the lower side, then the flow has to turn exactly by angle phi. So from the geometry of the airplane and through this analysis, you can know exactly how much pressure is on top and bottom of the airplane. So let's try that. Okay, so this is the delta V, and through the conservation equation, we have rho infinity times u infinity times sine of theta. So that's mass flux per unit area, right? And that mass flux times the delta V, which is u infinity times phi divided by cosine theta. That's the difference in momentum flux. Normal to the shock. What's different from the momentum equation normal to the shock and the momentum equation tangential to the shock, as you remember, is that the pressure force is in the normal direction. So there is no actual term for the tangential conservation of momentum. That is why there can be only a zero velocity difference in the tangential direction. But for the normal direction, it's not going to be zero. So this thing is going to be equal to the pressure force per area. What is that? It's delta P, right? Right? The pressure force per unit area is basically the difference in the pressure upstream and downstream. Agreed? Okay. So now, basically, just to simplify that a little bit, so that's the rho infinity u infinity squared, and that's basically tangent of theta, right? And then this phi. That's equal to delta P. You can do exactly the same analysis for a flow that turns down. So if I have another what we call expansion wave, that's like a reverse shock wave. An expansion wave is actually different from a shock wave in the sense that it's finite thickness, right? The flow kind of turns an angle. But for small disturbance theory, it doesn't make any difference because basically there is almost a zero pressure loss in both cases. And for an expansion wave, the pressure decreases and the flow in the normal direction would increase as a result. Right? So you have exactly the same set of equations, except for the only difference is phi is going to be negative, right? The angle, this angle increases, so we get the theta plus an angle, right, instead of minus. And delta P is going to be a negative quantity, so the pressure would decrease. But anyway, so this equation would be exactly the same, no matter for shock or for expansion waves. Okay, this basically tells you a very nice linear theory that relates the geometry of, for example, an airfoil or an airplane. I mean, this is a two-dimensional analysis. In three dimension, the thing is a little bit more complicated. But like, let's focus on 2 dimensions for now. In 2 dimensions, if you have an airfoil that looks like this, okay, we know the angle of the flow, right? Basically, there are waves that comes out of the airfoil, and the streamlines are exactly going to be the shape of the airfoil on the upper and the lower face, except for translated along these lines. So basically, these would be exactly the streamlines. It just follows the contours, except for translated with that theta angle. Okay, and from this angle, you would know exactly what is going to be the pressure at the upper and lower sides of this airfoil. So if I know this point has an angle of phi, I know the pressure at this point is going to be exactly like, actually, let me just say Cp, because this rho infinity u infinity square, if you multiply by half, right, it's gonna be the non-dimensionalization coefficient for Cp. So that's exactly equal to 2 times tangent theta. Oh, by the way, tangent theta is because we know theta is equal to arc sine of 1 over m, tangent theta is actually going to be what? Tangent theta is going to be 1 over square root of m squared minus 1, right? If you have a triangle whose sides are m, 1, and this side has to be m squared minus 1, right? So tangent is going to be 1 divided by square root of m squared over 1. All right, so CP is equal to 2 times, let me just write over this, 2 divided by square root of m squared minus 1 times phi. So let's just intuitively look at what this tells us. At the leading edge, when we have a high angle, we have a high CP, right? As we move to the middle of the airfoil, where the airfoil is tangential to the free stream, we have CP exactly equal to what? Zero, right? I mean, phi is equal to 0. So what's happening is that the pressure would increase by this changing angle, and as the angle changes back to 0, the pressure would decrease, right? Delta P is exactly proportional to the change in the angle, right? This is really the changing angle. So basically, because of the linearity of this formula, we can just accumulate the changes in angle, no matter if the change is positive or negative. When the total change of angle is going to be 0, the total change of pressure is going to be 0, right? So pressure would be exactly equal to free stream at this point. Now, as you move further downstream, the angle keeps decreasing, and the pressure would then keep decreasing, right? So what does that mean for this airfoil? It means a drag, right? The pressure is higher over here, lower over here. So the pressure is higher in front, lower at the back. So this is the nature of the drag in supersonic speeds. Is actually fundamentally different. Okay, on the lower surface it's the same, except for the ratio is reversed. When you're turning downward, the pressure increases. When you're turning upward, the pressure decreases. Again, at the parallel point, you have 0 pressure. At 0 CP, right? The pressure is equal to free stream. As the angle turns upward, you have lower and lower pressure. So on both sides, you have higher pressure near the leading edge when the airfoil thickens, and you have lower pressure near the trailing edge when the airfoil thins out. That gives you drag. Okay, and what's more interesting is the magnitude of the drag. The magnitude of the drag is actually relates to 2 things. One is, what is the delta P? The delta P is proportional for the same chord. The delta P is proportional to the angle, which is proportional to the thickness, right? It is also proportional to how much, basically you have higher pressure, but the pressure works in this direction. So the component in the drag direction has to be multiplied by another angle. So the total drag is proportional to the difference in pressure times the angle again, and the difference in pressure is proportional to the angle, right? So basically the total drag is going to be proportional to the square of the angle, which is going to be the square of the thickness to chord ratio. All right, so basically the total drag is proportional to the square of the thickness to chord ratio. This is another thing that's very prominent in supersonic designs. If you look at supersonic airplanes and wings, they have very slender fuselages compared to subsonic airplanes. They also have very thin wings compared to subsonic airplanes. These all relates to the square effect, right? If you thicken the wing by a factor of 2 and you thicken the airfoil by a factor of 2, you get 4 times as much drag. Similar analysis can reveal you the lift. So if you change the free stream, introduce an upward component, you are going to have less turning in this part, right? Because the free stream comes upward in the beginning. You have more turning over this part. So you have higher pressure in the bottom, lower pressure on the top. That can also reveal you how much lift you get at supersonic speeds. I mean, all of these are very useful when you're designing airplanes and airfoils at supersonic speeds. All right, so basically this is really the fundamental principles of how do you do analysis, like the basic analysis at the supersonic speeds, is that you can correlate the pressure with the flow angle. And the flow angle relates to the geometry of the airplane. Now from the pressure, you can integrate and obtain lift and drag. All right, and in certain sense, this is actually a lot easier than subsonic flows. It's actually more intuitive, right? And yeah, so that's what we are covering for transonic and supersonic flows, and we'll touch a little bit more about it when we are working on our project.